Hey guys, welcome back to day two. We're going to be talking a little bit more about linear correlation and things like that. We're going to take a look at a set of data and we are going to learn about a new type of hypothesis test. We're going to take the things that we know about hypothesis tests and apply it to the stuff that we were talking about yesterday with linear correlation. All right. So we've got a new test that we're going to be learning about and a new distribution, a new sampling distribution as well that we're going to be talking about and exploring a little bit. And we'll do a couple of examples and see how those go. All right. Our data that we have here, we're looking at temperature and we're looking at tardies. So we're trying to establish whether or not there is some kind of relationship between the temperature outside and the number of students that are late to first hour at school, right? Who knows? There might be a relationship, there might not be, but that's our goal, is to kind of find out if there is any kind of relationship between these two variables. And then if there are, can we use it to make a prediction? Can we predict the number of tardies based on the temperature outside? Right? And we're gonna look for that relationship using a significance level, right? Because like I said, we're gonna be using a hypothesis test. We're gonna be using a level of significance of 10% here. All right, so is there a correlation between the outdoor temperature and the number of tardies at a 10% level of significance? All right, so we're first gonna start investigating this by looking at the scatter plot and doing just a regular linear regression to look at the correlation coefficient between these two variables. All right, so I'm going to go to my calculator, I'm going to turn it on, and I'm going to go to stat, and then I'm going to go to edit, and I'm going to put my data from these two things into L1 and L2. All right, so what we're going to do is we're going to let temperature represent the X variable. We'll let tardies represent Y. So that means this will go into list 1. The tardies will go into list 2. All right, so go ahead and pause the video and take a minute and enter this into your graphing calculator. All right. So hopefully you've got your data entered into L1 and L2. We're going to go ahead and take a look at the scatter plot. That's what they want us to do first, is to take a look at the scatter plot and just do a visual observation of whether or not we think there is some kind of correlation between these two variables. So let's go to second stat plot here in blue. So second y equals. We'll turn on stat plot 1. And then we are going to select the scatter plot option here under type. You want to tell it that your data is in L1 and L2, and then we'll go ahead and do zoom option 9. And we're kind of looking at this thing, and I'm just based on observation here, I'm not seeing a whole lot going on. I don't see a line really forming. We've got points all over the place. But let's go ahead and get the line up there just to make sure we can see how far away from the line these points really are. All right. So the next thing I'm going to do is I'm going to go to stat, I'm going to go to calc, and I'm going to go to option number 4 here, which is lin reg. It's a linear regression. Okay. And I'm going to, again, tell it that my x variables or my x values are in L1, my y values are in L2. And then under store EQ, I'm going to tell it to plot the line. So I'm going to go green, right? So yesterday we talked about this. You go to the green button and then trace. And then you can select option 1 for Y1. It'll input your regression equation into Y1 and graph it. So I'll go ahead and hit calculate. See what I get. And I'm going to hit graph. And there's my line. You can see it has a very small slope. It only went up just a little bit here. And you can see the points are scattered everywhere. All right, so I'm going to go ahead and I'm going to comment on the strength and direction of this. For the strength, based on what I'm seeing in the scatter plot, we are seeing a very weak correlation between these two variables. And the direction, if there is any direction, is going to be positive. Okay, so in other words, as the temperature increases, perhaps so do the tardies. But that's about all that we can say here. So let's go ahead and find the correlation coefficient from the sample. So I'm going to go back to my home screen. I'm going to go to Stat, Calc, and then I'll go down to option 4 again, and I want to look at the R value, right, that correlation coefficient. So I'll hit Calculate. And you'll notice that I'm not getting my R value or my R squared value from this, and that is because I did not turn on my stat diagnostics option here. So you have to hit Mode and go to Stat Diagnostics and make sure that it is selected in the on position. Okay, so I'm going to change that to on and then rerun that linear regression, and we'll get our R value. Okay, so it is now turned on. Let's go to Stat, Calc, option 4, and we'll calculate one more time. So now we have our R value, and it's 0.004, right? I'm just going to write that down here. So R equals 0.004. So this is a number that's very close to 0. And if you remember from yesterday's notes that if we do have a correlation coefficient that's very close to 0, it would suggest that there is no correlation between these two variables. Okay, but we're going to go ahead and run what's called a hypothesis test for this to verify at a 10% level of significance that we do not or do have a correlation between these two variables. All right, this is how we formally do it in statistics before we can make any predictions, before we can talk about the relationship between two variables. We run a hypothesis test to make sure. Okay, so if there was if we were suspecting that there were a correlation between these two variables, at what point do we feel that it's a strong enough correlation to actually use it to make predictions? Is it going to be at 0.5, 0.6, 0.8, 0.9? Where does that happen? And that's what the hypothesis test helps us to do. Is it draws that line where it says, if we get a correlation coefficient that is this big or this close to 1, we're going to go ahead and use it to make predictions. All right. So to do that, we have to run something called a Lin-Reg t-test. All right. So this is our new hypothesis test here. And we're going to talk a little bit about its background. All right. So one of the first things we want to talk about is just notation, right? So what is the symbol that we use for the correlation coefficient? We use a lowercase r, all right? So make sure you're using the correct notation and the correct symbol. Would we calculate this from a sample or from a population? To calculate this comes from a sample. We would make observations, just like we did up here. We had a sample of about 13 temperatures and 13 days worth of tardies, and that's where this value of R comes from, right? But let's suppose for a second that I went and observed a different 13 days. And would we expect to get the exact same correlation coefficient? And the answer to that is no, right? We would not, right? We would maybe get something close, or you would hope that you would get something close, but every time you take a sample of 13 days, you're going to get a slightly different correlation coefficient. You're going to get something that's a little bit different every single time. All right, with different samples come different numbers generate different R values. All right, but if I take those R values, if I do a repeated sampling over and over and over again, and I take those R values and I created a histogram with them, I would get a distribution. This is called a sampling distribution. We talked about this for the mean and the proportion, and it turns out that the correlation coefficient has its own distribution. And I want to take a couple minutes to talk about the shape, center, and spread of that sampling distribution, and then we'll be done with it, because we're going to get to a point where we're going to use technology for this thing. But it's good to know where the technology is drawing from. All right, so let's talk about this a little bit. The sampling distribution of the correlation coefficient R itself has its own distinct shape, center, and spread. And in fact, it has many different distributions because the distribution changes based on certain things. All right, so let me show you what I'm talking about. All right, so what we're looking at here, this is an automated program that is going to take several different samples of whatever size that I specify, and it's going to take those samples from a population with an expected correlation coefficient that I also specify. So when I said before, when we were talking about this R value over here having many different distributions, the reason that it has so many is because the distribution changes based on whatever the population correlation coefficient is, and it also changes based on our sample size. So watch what happens here. So what I have going on is I have a population correlation coefficient of about 0.13, and I'm going to try and change this to be as close to 0 as possible so we can see we're going to be pulling from a population that has two variables that are not correlated at all by getting as close to 0 as we can here. Okay, so there we go. So that's pretty close to 0. And what I'm going to do is I'm going to make 10 observations at a time. So I'm just going to repeatedly take 10 samples of data for X and Y, and I'm going to calculate a correlation coefficient, and then I'm going to distribute them down here. All right, and we're going to see what that distribution looks like. So watch closely. There we go. You can kind of see it like it's bouncing around. That's because it's constantly updating the histogram because it's repeating those observations over and over again. All right, and I'll go ahead and hit stop. And we can look at the shape, center, and spread here. All right, so shape is obviously normal, all right, and that's we're centered around what we expected the correlation coefficient to be. So the population correlation coefficient matches up with the sample correlation coefficients here. So it should be centered around 0. All right, and we can see it's spread. Let's see if we can change the spread a little bit. Let me show you how to change the spread. And we're going to increase the number of observations here. I'm going to increase the number of observations to 30. All right, so in other words, my sample size is going up to 30. So I'm going to be observing 30 days at a time. So I'm going to do 30 and then another 30 and then another 30, and I'm going to calculate correlation coefficients each time, and I'm going to distribute them, and let's see what happens. And stop. All right, and you'll notice what happened to the curve is it got a lot skinnier. It's still very normal. It's still centered on 0, but it got a lot skinnier. All right, so the spread reduced, or the variability reduced, because the sample size went up. All right, and this is not uncommon. We've seen this before with the other sampling distributions, so you're probably sitting here wondering, like, why are you showing this to us again? Well, watch what happens, because there's another thing that controls this distribution, and it is our expected correlation coefficient. Let's say we increase the correlation coefficient to something like 0.6, all right? So we're increasing the strength of the correlation in this population, all right? I'm going to put the number of observations back down around 10, all right? So we're going to be grabbing samples of size 10, and we have increased the expected correlation coefficient from 0 to 0.6. So let's see what happens here. And stop. And so take a look at what happened here. So if we look at the center, right, we expected 0.6. The center of this distribution is clearly at 0.6. And look at the shape. It's no longer normal. It is skewed off to the left. And the reason that that happens is because correlation coefficients can't be any bigger than 1. So it's got a lot of room to spread out and and have variation over here on the left, but it doesn't have a whole lot of room over here on the right. So it automatically skews as the population correlation coefficient gets closer to 1. All right, and watch what happens if I increase this up to, let's say, 0.8, and I resimulate, grabbing samples of size 10 over and over again, and notice that it skews even more. It's even more skewed to the left. Now let's watch what happens when I make this thing go negative, right? So I'm going to go with a negative correlation coefficient. So I'm going to move it off here to like negative 0.6, and let's run that simulation again. And there it is. Okay, so now it's skewed over here, because remember, the correlation coefficient can't be any less than -1. So not a whole lot of room to spread out over here, but lots of room to spread out over here, making it an automatic skew right. Okay, so hopefully what we're getting from this is that the distribution of this correlation coefficient changes. There's so many of them. Kind of like the t distribution, we have to adjust every time we have a different correlation coefficient from the population in a different sample size. The shape of this curve changes, which means when we try to go and get the area underneath the curve to calculate a probability, it changes every time either of these two things change. All right. So we have to take that into account every time. It's not as simple as going to the normal distribution like it has before. All right. This is why we're going to let technology do this for us. We're not going to do this one by hand like we have in the past. All right, so we can rely completely on technology for this simply because it's a elementary statistics class, it's an intro class, and the by hand calculations are very tedious and very long. All right, so let's take a look at this thing called the Lin-Reg t-test. All right, and we're going to set up a null and an alternate hypothesis just like we always have. All right, so for our null hypothesis, oh wait, one more thing. We need to talk about the parameter for the population correlation coefficient. So for the sample, we used R. So for the population, we're going to use the Greek equivalent of R. And this might make you a little upset, but it is this character right here. Looks like that, right? It's a P with a big, huge loop for a tail, and it's actually considered rho. All right, this is the Greek letter rho. and I will try and accentuate that tail. It looks like a P with a big tail, essentially, is what it is. And if you look at it in the textbook, it's not this accentuated, but that's what it is. I don't want to get it confused with the proportion, and I don't want to get it confused with probability. So I want to make sure that this symbol is somewhat unique so we don't get it confused. All right. All right, let's set up the null and the alternate hypothesis here. All right, so for the null hypothesis, this is real simple. We're always going to say that the population correlation coefficient, or what we expect the correlation coefficient to be, is 0. Okay, there's my symbol, and I'm going to say that the correlation coefficient is 0, meaning no correlation. I expect there to be no correlation. All right, now if there was correlation, the population correlation coefficient would be not 0, right? It'd be something like 1 or 0.8 or 0.9 or something like that, right? So our alternate hypothesis is going to be the contradiction of equaling 0, which is not equaling 0. So if it doesn't equal 0, if we get far enough away from 0 in either direction to -1 or +1, we would say there is a correlation. Okay. I don't know why I put 0.05 up above. I said 0.1, so we'll stick with 0.1. And I'm going to put 0.10 here for our significance level. All right. So now I'm going to go to my calculator. I'm going to run this thing called the Lin-Reg t-test, and I'll show you where that's at. Okay. So we're going to go stat. We're going to go over to tests, and we're going to scroll down until we see something that literally says Lin-Reg t-test. And it's in here. There it is. So it's option F. It's all the way down at the bottom. I'm going to hit enter, and you'll see the things that it asks for. It asks where your data is, where are your X values, where are your Y values, and we stored those in L1 and L2. And then it's going to ask you about what kind of a test are you running. It is possible to run a left tail or a right tail test on this, but something you guys should know, for every single problem that we do in here, we are always going to run the two-tail test. We're always going to set up our hypothesis test just like this over here. Okay, it's always going to be equal to 0, not equal to 0. No correlation is our null, correlation is our alternate. All right, and I'm going to go straight to calculate. All right, so not a whole lot of stuff to enter. It's gonna know our sample size by looking at L1 and L2. It's gonna be able to calculate everything it needs from the raw data. All right, and it'll run. And we get a lot of stuff. All right, so we get this t-value. This is our test statistics. I'm going to write that down. 0.016. And again, this says the same thing that it always has in the hypothesis test, is it tells us how many standard deviations away from the expected value we are. So we're about 0.016 standard deviations away from 0, which is not very far, right? Which is what we expected because we didn't expect there to be any correlation. So we didn't expect to get too far away from 0. So what is the probability of this happening, right? That's what the p-value tells us. And we get our p-value right here. So there's a 98% chance. I'm going to say my p-value is 0.98. So there's a 98% chance of getting this test statistic by random chance. All right. So the p-value, All right, what does it tell us? Well, scratch that. 0.98 is certainly greater than 0.10, which is our significance level. So we fail to reject. We fail to reject the null hypothesis. We can't reject that there is no correlation. All right. So the question is, should we use the LSRL? Should we use this model to make predictions about tardies? And the answer to that is no, we should not. There was not a strong enough correlation. I proved that with the hypothesis test. We should not be making any predictions using the temperature for the number of tardies. All right. So that's what one of those tests looks like. It's not too hard. I know I talked a lot about a lot of like abstract stuff and whatnot, but really what you're going to be doing is you're going to do this hypothesis test, which is completely on the calculator. All right. Let's run one more. So we got the next page here. We'll do one more so you can see it run all the way through. And this time what we're looking at is we have 11 statistics students. They took a test. So they took their third exam, and these were their scores on the third exam. And these were their scores in the final exam. And so the question I'm trying to ask is, can I use the third exam score to predict what they get on the final exam? All right. Now the third exam was out of 100 points. The final exam was out of 200 points. So that's some background on those scores. And I'm trying to figure out how strongly correlated these things are. All right. So I'm going to go to my calculator. We're going to go stat, edit. And you'll notice I already have my data in L3 and L4 here. If you want, you can clear out L1 and L2 and put your new data in, but go ahead and pause the video, put that in, and we'll continue on. All right, so again, for me, I have my data in L3 and L4 here. So I'm gonna go right to my scatter plot. So I'm gonna go to L1 here. I'm gonna make sure scatter plot is selected, and then I'm gonna tell it where my data is. And remember, my data is now in L3 and L4. Okay, and I'm going to do a zoom with an option 9. And okay, so there we go. So it looks like we have a pretty good linear correlation going on. I can visualize where that line of best fit is going to go. It's going to go about right here with maybe one outlier kind of off far away from the line, but most of these points are going to be centered around the line. So visual inspection here, right, just describing the strength, direction, and form. We saw a linear form to it, and the strength here was strong. It looked like it was a pretty strong correlation, and its direction was positive. It was going up and to the right. And so we had a positive direction. All right, so I'm going to run a linreg here just to check its correlation coefficient. So I'm going to go stat, calc, option 4, and again, I'm going to change my list to list 3 and list 4. And just for fun, I'm going to go ahead and put that line in there so I can see it. There we go. So we have a correlation coefficient of 0.66. Interesting. All right, so I'm going to go down here. All right, so we got an R value of 0.66, and it looks stronger than that, honestly. Let me look at that scatter plot one more time. So I'm going to go to graph. It should put the line in there for me now. Yeah. I wonder if it's this particular data value here that's kind of throwing it off, but most of these points are pretty close. These ones are a little far away. Maybe this one's a little far away, but for the most part, it didn't look that bad. All right. So what does it suggest? I'm going to say maybe a strong correlation. And this is kind of what we do. I mean, we try and make predictions along the way and gather as much evidence as we can to establish that correlation. So it's kind of iffy, right? 0.66, I'm not sure if that's strong enough to be making predictions with. So this is where the hypothesis test comes in very handy. It's going to tell me whether or not I should use it to make predictions. So just like on the front page, I'm going to set up my null and my alternate hypothesis the same way. Okay, so my population correlation coefficient, I expect that to be 0. All right. And my alternate hypothesis to that would be that it is not 0. Okay, so we have a not 0. And we're going to run this at a level of 0.05. All right, so our significance level here is going to be 0.05. Then I'm going to go run this hypothesis test on my calculator. So I'm going to go stat. We'll go over to test, and it was option F. So I got to scroll down, or you can hit alpha F and it'll take you right to it. There it is. Hit enter. Again, I got to tell it where my data is. So I'm going to tell it that it's in list 3 and list 4. Go. And again, just make sure the not equal to 0 part is selected here. We'll be selecting that every time for these types of problems. We'll hit calculate, and here we go. So our test statistic was 2.658. Right? So we'll say T is 2.568. So we're about 2.568 standard deviations away from our expected correlation coefficient, which was 0. So that's pretty far away, and the probability of that happening by random chance is 0.026. Right, so we got 0.026 for our p-value. So I'm going to compare that 0.026 to my significance level 0.05, and we are less than 0.05. So that 0.66 was strong enough. So should we use the least squares regression line to make predictions about tardies? Yes, we should. There's enough evidence to establish a linear correlation between those two variables. All right. So since we ran our hypothesis test, we should go ahead and make a prediction, right? So what would the best predicted score in the final be for a student who had a score of 75% or a 60 out of 80? All right. So let's go back. We have to get our equation, right? So it gives us our equation in a plus bx form. So the slope of our line is 4.82. So we'll say y equals 4.82x plus, and let's get our this a value, which is our y-intercept, so negative 173.51. Right? And our score was a 60, right? So I'm going to be plugging that in for x. So we'll say y equals 4.82 times 60 plus a negative 173.51. So let's crunch that in our calculator real quick. So we got 4.82 parentheses 60 and then minus 173.51. There we go. So this would be our final exam score, right? So we'd say y equals 115.69. So we would predict a score of 115.69 on the final exam for this student. All right, guys. That's enough for today. So you saw 2 examples of that Linreg t-test, and I talked about it in depth, probably more so than I needed to. Hopefully I didn't bore you to death. But yeah, give it a try. There will be some problems like this on the homework. And again, as always, let me know if you have questions. Send me an email and we can run through it together. All right, guys. Have a great day.